Tonight I will present our work on self-stability and robustness for a fast bipedal running model. And so I've been looking at open loop stability for bipedal running, mostly without inertial measurements, and with the idea that if we implement intrinsic dynamics in a way to have intrinsic stability, that we can make the robot lighter, more efficient, easier to control, and in the end make the robot run faster. And one example of that is the Planar Elliptical runner, which was developed at IHMC. And this looks really slow, but it's 10 miles an hour because it was slowed down 33 times. This robot runs without any measurements. There is a single electric motor that's operator controlled to a certain voltage, and that voltage determines in the end how fast it runs. It's tuned to match the treadmill speed. And basically the goal was understanding what makes this robot stable. There were some intuitive explanations, but there wasn't any foundation to it. And to do that, we went to simulations, and the TSLIP model has been used extensively to model center of mass dynamics. But we needed something more. We extended the model with a trunk to include the body pitch stabilization effects. And in the flight phase, the leg is reset relative to the body without an inertial measurement and given an angular retraction rate. And we've investigated the effects of running speed, parameter choice for leg length and mass offset, leg stiffness, leg length was normalized, passive trunk stabilization, effects of damping. And we mostly focus now on trunk stabilization, as we found that if we have the center of mass below the hip point, we passively stabilize the body pitch, and we find numerically stable, be it neutrally stable gaits. And we get back to the virtual pivot point strategy for stabilization, which has been mentioned before. And we think the most important part is not that the ground reaction forces converge to this single point, but that there is a restoring torque. And that torque is mostly generated if the ground reaction forces do not move too far from the hip point as the pitch is perturbed. So we approach stabilization as would a virtual pendulum, a wheel with an off-center mass, or as the metacentric stability that stabilizes a rolling vessel. And we combine those with the running model, and we find that in the passive model, if we perturb the body pitch, the ground reaction forces remain directed towards the hip, and thus generate this pendulum construction, this metacenter that stabilizes body pitch. Now, of course, we also want to understand what happens with the planar elliptical runner, which is similarly constructed to the model, which has a hanging mass, a hip point, and the foot with an elastic element which is directed towards the hip. And we model the electric motor with a constant angular velocity controller at the hip, which implicitly is a velocity controller in global coordinates because of the predictable interaction between the leg and the ground. And the damping in the leg is used to model energetic losses in the actual running robot. And the leg is locally defined, as is the kinematics of the elliptical runner. And we find a model that runs, that is asymptotically stable, robust to step-down disturbances, body pitch disturbances. And we find that if we tune the parameters correctly, we get a pretty close representation to the step average results of the measurements on the elliptical runner. There's a lot more, especially in the velocities, there's more variance in the measured signals. But on average, the trajectories, especially in the stance phase, match pretty closely. And if we take the model and apply the same pitch disturbance as before, we find a structure that is similar in the virtual pivot point. So that concludes that we can passively stabilize body pitch. Oh, bad. I can. So we find the similar metacentric stability that passively stabilizes the body pitch, and thus the metacentric stability may explain how the planar elliptical runner is stable. Thus we can passively stabilize body pitch, especially through the design and directing the ground reaction forces mechanically. And this enables bipedal running without inertial measurements. Now the next step is breaking the robot free from its planarizing walls and extending the self-stability into 3D. And that concludes my presentation.
Questions? Ah, yeah.
So you can't change angle of attack really, but there's passive adaptation of angle of attack, I'm guessing. Are you observing big changes of effective stride length eventually, or
What exactly do you mean?
so your planar runner
Yeah.
has a fixed trajectory.
Yeah.
So therefore you have a fixed stride length.
Yeah.
And is your model and your simulation, is it optimized for that? And you never look beside like shorter strides, longer strides?
We tuned the simulation to match the results from the elliptical runner, but we have also explored different stiffnesses, different speeds, which include different stance length, different flight phases, different stride lengths. We find that the planar elliptical runner is right in the middle of quite a robust parameter region. Does that answer your question?
If the center of mass offset is forward,
Yeah.
how about the torque? How do you say the sum of torques? Is it still 0 over a whole stride? You see what I mean? The forces look like kind of symmetric, but
Yeah.
the center of mass is forward, so it looks like there's more momentum that would make it tilt forward.
If the center of mass is forward of the hip, that's because there's energetic losses, and there needs to be some compensation for the energetic losses, which is the damping in the leg as we model the elliptical runner. And if it's forward of the hip, during the stride, the body will tilt a little more forward and then fall again during the flight phase and bounce a little bit.
Okay, one more question while we get to the next speaker.
How do you plan to extend this into 3D?
I've been exploring a couple of options, and right now with point feet, we've been not very successful. One solution might be to include an ankle torque. One is looking at suspending the hip with a pivot point in a roll direction, but we're not sure yet.
Okay, let's thank the speaker.